I'll be saying elementary things which all of you already know perhaps, with just a repetition maybe. Okay, so don't worry. I'll be saying very simple things, not even renormalizability of the QED. Okay, so forget about standard model. Okay. Again, I'm afraid of giving the title of this lecture, so there is no title. Okay, so it's just I'll be doing some loop just a illustrative example. Let's say one loop calculation in QD context, and then try to explain what it means by renormalizing something. Okay, the field and couplings and all that, and let's see how far I can proceed. I may be ending up at the middle of nowhere. Okay, so don't worry. Okay, so again, let me give this thing that is, I think I have to write little big. Renormalization of QED. Okay, so my starting point will be this particular thing that we use or that we compute in an interacting quantum field theory, okay, which is this thing, the endpoint correlation function, time ordered, okay. And this quantity can be calculated in an interacting quantum field theory where your, is this visible? Okay. Yeah. So in a interacting quantum field theory, if you have a free part of a Lagrangian and the interacting part, you can compute this quantity in perturbative quantum field theory, order by order. Okay. The thing that I'll be interested in for the moment is this particular quantity, which is the 2-point correlation function of, let's say, electron or the Dirac involving Dirac field. Okay, and in the context of QED, so my L is, I think I can write it here. So my L is the QED Lagrangian, okay, which is minus 1/4 f mu nu plus psi.
The chair is not for you, but for the tasker.
Yeah, okay, thank you. Okay, so this is the Lagrangian and this is my L interaction. If you recall that the expression that I wrote earlier, that in perturbative quantum field theory, we can calculate this. There is a, in terms of the interacting field, in terms of the field in interaction picture, and calculating this time order product of those field in interaction picture in a free theory vacuum, right? But the effect of all those things, which I do not want to write right now, those big expression, is basically this result will be sum of all the diagrams with two external lines without the bubble diagram, right? Okay, so if you draw the diagrams in the context of QED, this will be This will be given by all these diagrams. Okay, let's say this is x, beta, alpha, and so on. At higher order, you will get all these other diagrams. Okay, let me just draw maybe one more. This will be another diagram at higher order. And so on. Okay. Many other diagrams, there will be 2 more diagrams at this order, okay, and then higher order diagrams. This thing can be systematically written down using this notion called 1PI diagrams, one particle irreducible diagrams, which all of you perhaps know. So these are the diagrams. If you cut any internal lines of those diagrams, it doesn't give you 2 separate diagrams. Okay. So I'll just introduce this diagrammatic symbol. Okay. By the way, let me give this quantity a diagrammatic notation again. So I'll be giving this with a blob. Okay, x prime beta, x alpha. By the way, also I have chosen an arrow convention, okay, to draw this diagram. So these are the diagrams which are actually this particular diagram will be sum of all one particle irreducible diagrams. Okay, so these are basically collection of these diagrams. Okay, I'm not putting the indices. And so on. These are all one PI diagrams. If you cut any internal line of these diagrams, they don't give you 2 separate diagrams, right? So then this expression that we have, this diagrammatic expression of this 2-point correlation function, you can actually write it in this way. Okay, just let me use this quantity. So this thing, you can write it down, which is this 2-point correlation function in interacting theory. You can write it down in this way. Right. With 2 insertion of such 1 PI contribution, and so on. So this will get repeated. Okay. You can just I think either you already know. If you do not have done this thing, you can just go back and put this thing together. Okay. So let me write down the amplitude of this particular diagram. Okay. So this diagram has also, okay, before I do that, this is a position space. Any question? This is a position space diagram. I'll just, since I'll be only interested in momentum space amplitude, let me give the corresponding amplitude in momentum space. Okay, so for example, this quantity, let's say, if I draw the same diagram in momentum space, there will be labels, the momentum labeling. Okay. In all of this and so on, and this whole amplitude I'll be writing down using, so this I have to put using this Feynman rules in QED. I have to put all the factors. This is a propagator, this is some amplitude which you will be seeing what it is actually, and this is another propagator, and these are all free, this propagator all free theory propagator. Okay. So, and these are the diagrams in momentum space. So let me put all this. So this quantity is the, I'm just writing down the, sorry. I'm just writing down the amplitude of this whole thing, okay. I sigma p times SF tilde. So there are these two propagators on both sides, and this basically represent the amplitude of this kind of all these loops that are there. If you just kind of input this external legs, this will represent that part. Okay. So yeah. So here I have the same thing repeated many times, so it will give a geometric series, right? So one can sum that formally, because ultimately those things will have some certain will have divergences. So so this sum will be a formal sum in the sense that when you do actual computation, you do it in a regulated theory, not in a theory where this is with bare parameters and bare couplings. Okay, so if I call this, if I give this full propagator in the interacting theory a name, so this will be the in momentum space, all these thing will be replaced by a momentum level. Okay, so the momentum space 2-point correlation function, okay, the full theory correlation function, this quantity will be related to the free theory propagator and this additional contribution. Okay, so you can sum this whole contribution in a using this geometric series sum. Okay, and it will look something like this. I by p slash minus m naught minus sigma p. Okay. Up to this point, I think, is it okay? So this m naught was the this bare parameter that appears here. Okay, and sigma p one need to compute. Okay, so this basically tells you that the pole of the propagator gets a shift by this amount, right? So the basic task in any theory, for example, in this context in quantum electrodynamics, will be to calculate this quantity order by order. Okay, so the first diagram that we encounter is this particular quantity. Okay, I'll just write down the amplitude of this diagram. Let's say, so if we are interested in one loop renormalization of QED, okay, this is one basic amplitude that one finds to be divergent. One simple amplitude one finds to be divergence. It's a simple 2-point correlation function, and one need to see what is the how this quantity diverge. Let's say at large momentum, which will be called which is called ultraviolet divergences, and how to regulate them, and how to kind of either cancel them or absorb them in the redefinition of the field and parameters. Okay. So let's take only one diagram first. Okay, this particular one. So I'll be interested only the contribution to this sigma p coming from this one loop diagram. Is that okay? So this is the order E² diagram. So I'll be calling that quantity sigma 2 of p. Okay. So my I just one more thing. Let me just finish this part. I just forgot to mention is this thing that the physical mass of the particle, okay, for example for the electron, is no longer this m naught. Okay, it will be given by the location of the pole in this propagator in this 2-point correlation function. Okay, so let's say at p slash equal to m, this denominator vanishes, then the m will be the location of the pole. Okay. So the location of the pole will be determined, which will be also the physical mass. In fact, we will be taking that as a definition of the physical mass by the following equation, right? So it will be p slash, should be bigger, it should be where this denominator vanishes. So this is where, for which value of p slash this gives you 0 is actually the location of the pole. Okay. Another thing is related to this particular expression. Is I. There is a dot. Okay. The other thing is that if you try to expand this around this pole, okay, you can actually do that. The only thing, since we have not calculated this, okay, this sigma p, okay, once we calculate, we can check what kind of as a function of p, how does it behave. So for the moment, let me assume that this is at least near the pole, this is the analytic function of p. Okay, so one can expand that this sigma p near the pole, and if you expand this sigma p near the pole, okay, so it will look something like this: sigma of m minus d sigma dp slash. Okay, by the way, this is function of p slash. Okay, even though I'm writing p at p slash equal to m, and so on. So this is just a Taylor series expansion, and it's possible if it's an analytic function. In general, it's very difficult to predict this analytic behavior of this thing. But only one, I think, one thing that guarantees that there will be a simple pole, there will be a particle like we can have a particle like nature in this thing. It's by this general principle that you use and derive this Kellel-Neyman spectral representation, where it actually at least gives you at least one pole, right, which corresponds to the mass of the particle, and then you might have bound state and other things. So as long as that is guaranteed, at least near the pole, you can do a Taylor series expansion. Okay. And then if you just substitute this here, this quantity, this particular quantity near the pole will look something like this. So keep this relation in mind. This will look near pole, it will look something like okay, plus maybe some extra term. So now if it's just a substitution of this gives you this particular thing, and z can be also calculated. Okay, it's actually the residue at the location of the pole, and I'll call it, because this is historically called z2, so let me call it z2. Okay, and this z2 has an expression. This is given by this 1 minus d sigma dp slash at p slash equal to m inverse. Okay. So this comes if you substitute this thing. So there are other terms, but if you just substitute this and ignore the higher the term that is proportional to p slash minus m square and other powers, you'll have this behavior. Okay. And this is one of the things that will be most important thing in all the theories that we do actually. Okay. Whenever in the context of renormalization, okay, these are the quantities that we calculate, okay, and later on we'll see how these things will be important, okay, if I can complete this whole discussion. Okay, any question up to this point? Okay, so the next thing that I'll be doing, I'll focus on this particular one loop diagram, write down its amplitude, and try to maybe explain a few things, and also finally I'll try to write down the amplitude without going through all the steps. But in case you have any question, you can ask me at this point. I think I can erase this like that. Maybe. So let's take this diagram. So this is the diagram we are interested in. Okay. So let me give this momentum level of this internal lines. Okay. And then you have to write down the amplitude of this quantity. And so this is, let's say, SF in interacting theory, but up to order 2, okay, or at one loop, whatever you can think of. So this quantity is, so I sigma 2 of P, okay, which represents only this one loop 1 pi diagram, okay, and SF2 of P on that side. But this particular quantity minus I sigma 2 of P is the amplitude of the loop part only, okay, and it looks something like this, okay. Just use of simple Feynman rules gives you this amplitude. There is this undetermined loop momentum which we should integrate over all the range, over the full range, okay. I k slash plus m naught I k square minus m naught square plus I epsilon comma mu minus I eta mu nu k square p minus k plus I epsilon, and there is a gamma mu as well, right? One extra. No, let me see. Did I miss it? Yeah, there is a gamma mu. There is one gamma mu. Yeah, I think it's okay, right? Yeah, okay, fine. Yeah. Two things just I should mention here is this. One is I'm using the photon propagator in Feynman gauge. Okay, I'll quote the result in arbitrary gauge, and it turns out that the electron propagator, if we calculate in arbitrary gauge, is a gauge dependent quantity. Okay, I'll give you the result, but it should not be surprising thing that why a electron have a gauge dependent propagator, right? But we are talking about off shell electron right now. It's a correlation function that we are calculating. If we do it for on shell electron, it should not depend on the gauge. So the final result that we'll see when there is a gauge dependent propagator I use for this photon, if I put on shell condition p slash equal to m, this should be there should not be any gauge dependency on that propagator. Okay, so that I'll come later on. But let's keep that in mind. One more thing I should also mention here is that all these integral that are there, okay, these are all in the full range from minus infinity to plus infinity, and so this thing is, maybe I just quickly mention this. What I mean by this is this particular quantity, and this is slightly crucial. All this integration that we have, this d4k over full range, I mean by this statement is this quantity. Okay, so dk0, dkx, and so on. So all of them goes to minus infinity to plus infinity, but in this way, not in another way. For example, not two different. Let's say if you have lambda 1 and lambda 2, okay, and lambda 1 goes to infinity and lambda 2 goes to infinity. It's not in that way. Okay. In fact, if you use that, so this is already one kind of regulation that we are using. Basically, it's like Cauchy principal value we are using, because the theory has all this expression actually diverges in if you take lambda 1, lambda 2 and take them independently to infinity. And in fact, if you calculate this in free theory, this momentum operator, if you recall, okay, and the momentum operator has this this particular integration. If you have seen it, there is this k vector and there is a delta cube 0. I think if you, when you calculate this momentum operator in free theory, okay, this is a divergent quantity, this delta cube 0, and you have a k here, okay, and you use this argument of odd function or whatever, then you set it to 0 so that the ground state doesn't have any momentum. This is strictly not true if you use this kind of lambda 1, lambda 2 and take them independently, because this is not a proper integral. This is a proper integral only when you have the limit from minus lambda to plus lambda and take the lambda tends to infinity limit, okay. Then only it goes to 0. Otherwise, it's a completely improper thing to do. So we have this regulator from the very beginning in the quantum field theory, and it's always a regulated theory. So keep that in mind. So I have this integral in that sense, okay. So this will help me to drop the linear term later on, the term that is linear in k in this numerator, okay. In fact, I'll use this odd function analogy and I'll drop them, but that's strictly possible when you have this thing. But anyway, that I'll do later on. Okay. So you can see there are this expression, for example, has already two kinds of divergences. One is in the large k limit when the momentum goes to infinity, okay, the power of the numerator and denominator, in fact, in this form, it's one should not check it in this form, but just naively, if I just say, you can see there is a k slash here. So the power of the whole numerator is, there is a d4k, so it goes like k to the power, so it goes like k to the power 5, the numerator goes, and then there is a k4, the denominator has a behavior for at high energy is k square and another k square here, k4, right? So it's like k to the power 5, and denominator has k4, so it's quadratically divergent, right? But the linear term will cancel precisely because of this thing that I told. So ultimately we'll see a logarithmic divergence in this, and we'll try to regulate that. First of all, any expression that is infinity is not possible to formally manipulate it. The best way to do this, or maybe I do not know whether it's the only way or not, is you regulate the integral, okay, you manipulate it and find the divergent piece and the finite piece separately, and then later on whatever you want to do with those divergence piece, whether you want to cancel, whether you want to throw the theory or not, that's up to you. But let's first do this manipulation using some regulator, okay. So what kind of regulator one can choose? There are various possible choices, okay. I'll be particularly using dimensional regularization, but let me just give a simple example where you will, let's say, where you have a similar such thing you encounter. For example, let's just consider a Euclidean integration, let's say in 2 dimension, something like this, okay. This also has, if you integrate over a whole range, it has a logarithmic divergences, right? So you can actually try to regulate this by maybe introducing a cutoff, sharp cutoff, okay. This is already a Euclidean integration, so I can just put the some upper limit and go to the, so you can go to the, so there is a 1 over 2 pi square, okay. So you can go to this radial and angular part, okay, in 2 dimensional, in 2 dimension, and it will look something like this. I hope I have it here. It will look something like this. D of p square. This is the radial integration that you are doing over 4 pi, okay. 1 over p square plus m square, and the result is all of you know is ln lambda square plus m square. And this is one way you regulate this, and you get you can recover the divergent piece by taking this to again to infinity, okay. One more possibility also that you perhaps all know is instead of this one, you consider a separate integration. So you subtract the infinity by introducing this thing called, so let me define an integral which is like this one. And you subtract from this another integral which is just similar expression, but m is replaced by capital M square. Okay. So this is this actually called Pauli-Villar's regularization. Okay. Effectively, what you are doing, this is a contribution that you are getting, let's say, due to some particle, okay, and you are getting a loop due to the let's say propagation of a scalar particle, let's say, in 2 dimension, okay, and you are subtracting a similar contribution maybe due to other field, and its propagator also look like a scalar, okay. The only difference is that the contribution comes with a negative sign, right? So in the context of Higgs, you have seen that the correction to the Higgs propagator for scalar contribution comes with one sign, and the Fermat comes with the opposite sign, maybe minus sign, right? So it's like opposite statistics, but it's still a kind of the behavior is like a scalar particle. Okay, it's not a physical particle, but you can interpret it in that way. Okay, and I think the result I don't know. It will go like something like this. Ln, ultimately this divergence will go like m squared by small m square. Okay, up to some factor. And it will also diverge if you take this m. Ultimately, it should decouple. So you should take this capital M tends to infinity limit, so that you have recovered the original integral, which was I. Okay, but then you encounter the divergence again. Okay. There are many other things, by the way, by which you can regulate this kind of integral, and you can look at this paper by Hitoshi Murayama. That's just a note where he discusses all other possible regulator. Okay, the one I'll be using is the dimensional regularization in this context. Okay, so I'll do this here, not in that simple example. Any question up to this point? I maybe not be able to complete this calculation either. Anyway, so the next, you can do one thing. You can at least, because it's a divergent integral, you can maybe regulate it fast. Okay, but some simple algebraic operation you can still do. In a divergent integral, you are not allowed to do many operations. For example, you are not allowed to do shift and all these things. Okay, at this level, so you can regulate it and you can go ahead with the manipulations. But this manipulation we can do, the manipulation of the numerator and denominator, little bit. Let's say I can take product of this thing. Okay, I can do that. And the famous thing that we use is the Feynman trick to combine this two propagator in the denominator. Okay, using this identity. Dx by ax plus b into 1 minus x square, if you have such factor. Okay, so let's say we combine this propagator using this trick, and then we also go to the d dimension. So I'll do all this together and write down the result. We also go to d dimension, so it will be d dk and so on. It will be 2 pi to the power d. So let me write down this expression. So minus I sigma 2 p, it will be minus I square d d k by. Okay, and let me write down the final result after. Okay, so and if you go to d dimension, the dimension of this quantity, okay, whatever it has, you are actually kind of increasing its dimension by increasing the power of momentum integral. Okay, So you should just take that can be taken care of by a factor of, let's say, dimensionful quantity. So this is the arbitrary dimensionful quantity that we are introducing in it, and in fact I can give it a name instead of this quantity, because I am calculating a completely different quantity in d dimension. Okay, so it looks something like this: dx k slash plus m, and you combine all the numerators and denominators in whatever way, it will comes out to be k minus xp whole square minus some delta, okay, and plus I epsilon. So now, since it's a regulated integral, you can interchange these two integral. You can redefine your momentum integral or momentum integration variable by a shift. You can call this to be new momentum variable or integration variable, this k minus xp. Okay. So this is now allowed because it's a regulated integral already, and this delta is this particular quantity. But this delta is m naught square 1 minus x minus x into 1 minus x p square. Okay. So let me just define this thing shift. Okay, k prime equal to k minus xp, and if you do that, I can replace this with k prime square. This is d4 k prime, because under this dd k prime, sorry, and this shift also gives the extra contribution in the numerator, and this is k prime slash plus xp slash plus m naught. Okay. Did I miss this gamma mu also? The gamma mu's are there, by the way. There is this extra factor of gamma mu. So you have combined the gamma nu with eta mu nu, and the factor of I in the propagator and the minus I in the photon propagator was also combined. Okay. So again, this is the even function of k prime. So you can throw away this this integral. Okay, k prime integration, and you'll be left with something independent of k in the numerator. And finally, so let me you have to evaluate an integral of this quantity involving this quantity. Okay. So dd k prime, numerator is independent of k prime, and this particular quantity. So let me just give the result for that integral. Okay, so no, not yet. Okay, one more step that you have to still do is not you have to do, by the way. That's what actually I want to emphasize here. Normally we do a weak rotation at this step, and because this is a Minkowski 4 vector, and k prime square is k0 prime square, and minus, let's say, mod k prime square, and in one of this integration, let's say k0 prime integration, will encounter a pole, right? And you have a I epsilon to regulate that, basically, right? So that there'll be, you have to calculate this, you have to do this residue calculation, right? You can actually do that. There is no problem of going through the residue calculation, but easier way, you can actually use weak rotation, okay, and then make it a Euclidean integration where you do not encounter the pole anymore. Okay, you can get rid of the I epsilon also. It's just basically this thing. So you have an integration like this, let's say, limit epsilon tends to 0 plus something like this, dx by x square minus a square plus I epsilon. You can do this integration using residue calculation, okay, and the result will be minus I pi by a. There is no harm in doing this, but you can use this weak rotation thing to do this also. What means actually, you choose a contour like this. So the poles are actually here and here, and you can choose a contour like this. Okay, and this contour doesn't include any pole. Okay, and because of this 1 over x squared behavior, okay, if you do this closed loop integration, this part of the contour will not contribute, it will go to 0 if you take this radius tends to infinity limit. Okay, ultimately you will be left with the integration along this line related with along this line, and it basically means this integral, if I use this contour, will look something like this. Okay, it will look something like this, minus I minus infinity to plus infinity dy by y square. I can actually break down this, but I don't have the time, I think. Okay, there will be I epsilon if you just make it a dz by z square minus s square plus I epsilon. Okay, and z along this line is iy, so z square will be minus y square, and I have taken all those factors into account. And this integral also I took on the other side. The range will be from plus infinity to minus infinity. All these things will be there. And since there is a z square will be iy, it will be minus y square, and this is minus s square. You can take the minus sign common. And then there is no pole along the y integration. Okay, so you can set this epsilon tends to 0 limit at this level, but not here because there is a pole. Without this is not well defined, but this is perfectly well defined. So the effect of all these things is that you encounter a factor of I maybe. This minus sign is typical to this particular case, it's not important. Okay, you have still a real variable integration over the real variable, okay, from minus infinity to plus infinity along variable y, which is a real variable, but somehow you have to replace this x with a minus iy, with a iy, sorry, and so the sign will change, right? So this is effectively the weak rotation. Okay, you will encounter a I factor in the measure. You will encounter, you have to replace everywhere z or x by iy, but your integration limit will be still over real variable from minus infinity to plus infinity. Okay, so this is what we mean by this thing. Any question on this part? So what I mean is just do this k0 prime. I will not write it equal to ik0 e. So this is a new variable I am introducing. Let's say I am going into a complex k0 prime plane. Okay, and this k0 prime is the real part of that complex k0 prime, and this k0 e is the imaginary part of that. Okay, so you are doing along that. So I will be just saying that not equal to, it's not a substitution in the integral. You should substitute this in place of k0 prime in the integrand maybe, and also in the measure, but the limit will be still minus infinity to plus infinity. Okay, so all this will be still valid. dd k prime will be I times dd ke. Okay, it comes from the k0 prime part, and this vector ke is k0 e and k prime. Okay, and k prime square since is k square. Okay. So if you do all these things in this integral, let me write down this integral part only. You will get this integral dd k prime by 2 pi to the power d 1 over k prime square minus delta plus I epsilon square. This will be equal to I times dd ke by 2 pi to the power d so you don't need this I epsilon anymore, okay, because there is no pole in this integral, and you get this extra factor of I, and all the integrals run over the real variable k0 e, kx prime, ky prime, and so on. Okay, and there is standard result for this Euclidean integration, and that's what that was the purpose actually. Just use the standard result of this Euclidean integral, just like this tan inverse x by a thing. Okay, tan inverse x by a integration. Okay, so this result, if you separate this into angular and radial part, the result will be this. One over delta 4 minus d by 2. So it's, as long as d is not 4, this integral is a finite integral, and if you take the limit d tends to 4, you have a gamma 0, and that actually is a singular quantity, right? So the original divergence of the integral was actually encoded in this gamma function. Okay, so you can actually expand this gamma function near the pole. Okay, d equal to 4, and separate the divergent piece and the finite piece in principle. I'll just maybe without going through any further of this thing, I can just write down. Maybe I don't have much time. This is the only thing I'll be able to maybe finish. So, any question on this part? Okay, so let me. So use all this. So to expand this around d equal to 4, you can just use this substitution where epsilon is a small quantity. Okay, and you write down all this. All this can be derived, by the way. Okay, 2 by epsilon minus gamma e plus some term of order epsilon. And you also combine all this 4 pi and all this capital and the delta and the mu square and all these things, you can get a combination like this. Maybe I can write down the final result without going through all these things. So in terms of epsilon, okay. So so this is 4 pi square order epsilon contribution and then you have this 0 to 1 dx x 2 minus epsilon. This comes from this gamma mu p slash gamma mu part, p slash plus 4 minus epsilon m naught part. Okay. Multiplied by this, if you combine all this 4 pi delta and all these things, this will give another factor. So now you can write down this this quantity. That's if you just find out the coefficient of the term 1 over epsilon, okay, which will going to diverge in the limit epsilon tends to 0. So let me just write it down. The divergent part only. Okay, this quantity is simply just take the coefficient and then do the x integration part. This term will not contribute. Remember, this delta is function of x, so this will not contribute in the integral x integration because only the first term is important. This multiplied by this epsilon will be finite. So the only contribution that you get for the divergent piece is this quantity. Plus finite term. Okay. So this is what you get if you use Feynman gauge. In arbitrary gauge, if I have the result, I will. If you use the propagator in arbitrary gauge, this will come up to be something like this. There will be a additional contribution from the gauge dependent part of the photon propagator. Okay, so it will be like I square by 8 pi square epsilon p slash minus 4 m naught plus p slash 1 minus xi times p slash minus m naught. Okay. If you put p slash equal to m naught, this contribution, this xi dependent contribution actually goes up. You recover this one. Anyway, so this is how you calculate this, which I have already maybe you did. The thing is that how to handle these divergences, right? In the redefinition of the field and redefinition of the parameters, let's say coupling and masses. So this will maybe renormalize the mass only of the electron, and then we go on and maybe computing the other diagrams which are also divergent. Without, of course, I cannot go into that thing. So, do I have time or shall I continue? Couple of minutes. Huh. Gamma? Oh, that expression? Yeah, this you have to use this expansion of this gamma function around the pole. Gamma? Oh, so value? It has a value. I don't know how from where this value comes from, but it has a specified value. Anyone has any idea how to find the value of the gamma E? No, that value I have, but I'm saying any idea how to get the value of this? Go ahead.
So when you have this gamma function, then basically as he has mentioned, they set d equal to 4 minus epsilon, right? So you have a gamma of epsilon. And apart from a Taylor series expansion, the Taylor series expansion you can write down in terms of divergent term and something called the digamma function. Okay. The digamma function's value at 1 equal to my gamma E. This is the origin of the digamma function.
Just a second. I have to with this. Anyway, have it. Okay, so if you recall, this is if using this you can calculate the Z2 that we have, right, which is 1 minus d sigma dp slash. Okay, you can calculate all these quantities. Forget this extra piece. Okay, and this will comes out to be, I think, 1 plus 8, 1 plus e squared by only the divergent piece of Z2, let's say. There will be finite piece in it. Okay, 8 pi square epsilon plus, the finite piece will be in the. And you can also, using this relation, you can also see how this physical mass near p slash equal to m, using this relation, okay, you can also calculate what is m, how m is modified with respect to this m naught with respect to the Bayer parameter. I think you will get something like this: 1 plus 3 e square by 8 pi square epsilon times m naught. So you see, the physical mass will be infinity if you take the limit epsilon tends to 0. Okay, unless you say that this m naught is not a fixed finite parameter, right, in the Bayer theory. Okay, if you think of this m naught is a fixed finite parameter, it has a fixed value. Okay, finite value, then the physical mass will be divergent. Okay, this only maybe makes sense if all these are yeah, anyway, can you get me from the back? Yeah. So if you treat this as a kind of unphysical parameter. If you take this to be maybe infinity, so that this combination is finite. This has to be your physical mass of the electron, right? So you treat this whole combination or treat this m naught in such a way that this product is found. Okay, this is one way of your interpreting that you are actually normalizing the Bayer parameter of the theory. But another way of this, because if you do a parametric calculation using the Lagrangian that I wrote, which has this Bayer parameter and Bayer coupling, and which are not fixed, which are not fixed, which doesn't have any fixed value. There is no, doesn't make any sense to do calculation in terms of those parameters, right? So better you write down a Lagrangian which has some fixed finite parameters, maybe the physical mass and the physical coupling, and you can actually so the method of bookkeeping will be this. So you rewrite the Lagrangian that we had earlier, but in terms of physical masses, let's say, or maybe renormalized masses and renormalized coupling, but adds additional counter term to the Lagrangian so that you cancel the divergences that you will encounter. Okay. So yeah, so recall this. So I'm just illustrating this with only one example, but there are other divergences that you need to calculate in this theory, which is the 3-point correlation function, the vertex function, and also the photon propagator. And so this was our starting point. Right. So not only this fields are Bayer fields, the couplings are Bayer coupling, and this doesn't make any sense in this way. So the 2-point correlation function that we calculated in terms of this field has this behavior already, right? We have seen this, right? This in the momentum space, the 2-point correlation function at one loop near the pole, it was something like this, Iz 2 by p slash minus. And this is already a divergent quantity. Okay. So instead of using psi, if you use this renormalized psi, let's say z2 to the power minus half psi r, and calculate the 2-point correlation function using this renormalized field, you can get rid of this z2 in the anyway, I don't think
Yeah, I think Chandran, you have to finish in the next couple of minutes.
okay. Anyway, I just promised you that I will be finishing in the. So, yeah, just finally I have to go through this. This Lagrangian in terms of, let's say, renormalized field and renormalized parameter and the counter term. So, yeah. Let me write down this, maybe at least this much, and then stop. So, you renormalize at all the fields that are there. Okay. So, this is in terms of so you have this Lagrangian in terms of so what I just did, I just replaced all the fields, let's say, with this, okay, and I have this extra term minus 1/4. This labeling that I am using is conventional labeling that people uses. and plus psi bar r delta 2 del slash minus delta m. I have not added all the counter term yet. What I did just is this. I just renormalized the field psi, and let's say if I calculate the photon propagator, I'll encounter the similar divergences, okay? And it will have, let's say, this iz3 by q square kind of behavior. And you renormalize only the field and this, and you replace this m naught. You split it into physical mass plus some extra delta m contribution, and you will encounter actually this, okay? What it actually gives you, this is not yet the full fixed Lagrangian that will give you finite result, okay? Even with this Lagrangian, if you calculate the 3-point correlation function with this coupling that I have here, I'll encounter further divergences, okay? The 2-point correlation function that I will calculate will be finite. For that, I have to fix this extra contribution that I wrote down here. Let me give you these relations, and then maybe I will stop. This delta 3 will come from the renormalization of the photon field, okay? The delta 2 is Z2 minus 1, and delta m is Z2 m naught minus m. So if you put this z here, Z2 here, you will get a multiplication factor Z2 here, and then you write it down as a physical mass plus extra piece, okay? So even with this theory is not finite. At the 3-point correlation function that you will be calculating, you will encounter a divergence again, okay? So somehow you have to then renormalize this particular parameter E0 that you have here, which is already multiplied by these two renormalization factor, but there will be additional factor, which is historically called Z1, okay? And once you do that and add the counter term for the 3-point correlation function as well, okay, then at one loop you renormalize the quantum electrodynamics by suitably adjusting this coefficient that I added here, okay? Maybe I can only stop at that level if you have any further question.
Questions?
Everybody knows this topic anyway.
If not, then let's thank Chandra once more. And we have some token of appreciation for his efforts to renormalize QED.
I apologize. The organizer gave me a very late notice and said that you have to discuss renormalizability of the standard model.
Oh, yeah. Now, it's okay?
Okay, now.
Okay.